It sat in antique shops for decades, glowing softly under black light, handled by collectors and admired for its color. Nobody worried about it. Nobody feared it. For most of its early history, this element was just a curious substance that made pretty glass. Then the 20th century arrived. And uranium changed everything. Uranium is a word that carries enormous weight in the modern imagination. We hear it and we think immediately of nuclear reactors, atomic bombs, and the particular kind of invisible danger that science fiction has spent decades associating with glowing green substances and catastrophic meltdowns. But before it became a symbol of anything, uranium was simply an element. A naturally occurring chemical element, identified on the periodic table with the symbol U and the atomic number 92. That number means every atom of uranium contains 92 protons in its nucleus, more than almost any other element found naturally on Earth. If you were to hold a piece of pure uranium metal in your hand, which is not something anyone does casually, but bear with the thought, your first reaction would probably not be fear. It would be surprise at the weight. Uranium is approximately 19 times denser than water. A piece the size of a tennis ball would weigh roughly as much as a large brick. It is a silvery gray metal, not unlike lead in appearance, and at room temperature it behaves chemically in ways that are interesting but not dramatic. The drama of uranium lies entirely at the level of the atomic nucleus, in properties that are invisible to the eye, undetectable to ordinary human senses, and were completely unknown to the scientists who first identified it. For nearly a century after its discovery, uranium was considered mildly interesting and largely harmless. The truth about what was happening inside those dense, heavy atoms was waiting to be found. The story of uranium's discovery begins in 1789, in the laboratory of a German chemist named Martin Heinrich Klaproth. Klaproth was analyzing a black mineral called pitchblende, a heavy, dense ore that had been mined in Central Europe for centuries, primarily as a byproduct of silver mining and considered largely worthless. During his chemical analysis, Klaproth isolated what he believed to be a new element embedded in the mineral, and he named it uranium after the planet Uranus, which had itself been discovered only 8 years earlier by the astronomer William Herschel. The naming reflected the scientific excitement of the era, a new planet and a new element, both adding to humanity's expanding map of the natural world. For most of the 19th century, uranium occupied a thoroughly undramatic position in the catalog of known elements. Its primary practical application was decorative. Uranium compounds, when added to glass or ceramic glazes during firing, produce a distinctive yellow-green fluorescence under ultraviolet light. Victorian glassmakers used uranium oxide extensively to create what collectors now call uranium glass or Vaseline glass, beautiful objects that glow vividly under black light and were considered entirely safe household items throughout the period. The complete transformation of uranium's significance began with an accident in 1896. Henri Becquerel, a French physicist studying fluorescence, stored some uranium salts on top of a wrapped photographic plate in a drawer, intending to use sunlight to stimulate the fluorescence and observe the effect on the plate. Several cloudy days passed, and he never conducted the experiment. When he eventually developed the plate anyway, expecting to find nothing, he discovered it had been significantly fogged, exposed, despite never having been brought into sunlight. The uranium had been emitting invisible rays entirely on its own, without any external energy source, penetrating the wrapping and exposing the photographic plate in the drawer. Becquerel had stumbled onto radioactivity, the spontaneous emission of energy from an unstable atomic nucleus, without the slightest intention of doing so. Marie Curie, working with her husband Pierre Curie in Paris over the following years, took Becquerel's accidental finding and built it into a systematic science. She coined the term radioactivity, established that it was an atomic property rather than a chemical one, and went on to discover 2 additional radioactive elements, polonium and radium, both isolated from the same pitchblende ore that Klaproth had analyzed a century earlier. The Curies and Becquerel shared the Nobel Prize in Physics in 1903 for this body of work. Uranium's story had become something far larger than a decorative curiosity. To understand why uranium matters so profoundly, you need to understand the difference between its 2 most important forms, what scientists call isotopes. Isotopes are versions of the same element that have identical numbers of protons in their nuclei but different numbers of neutrons. Because the number of protons defines which element something is, isotopes of uranium are all chemically uranium. But their nuclear behavior can be dramatically different. Natural uranium as it comes out of the ground consists almost entirely of two isotopes. Uranium-238 makes up approximately 99.3% of all natural uranium. Uranium-235 makes up the remaining 0.7%, a tiny fraction, but an extraordinarily consequential one. Uranium-235 is fissile. This means that when a slow-moving neutron strikes a uranium-235 nucleus, the nucleus absorbs the neutron and becomes so unstable that it splits apart, a process called nuclear fission. When the nucleus splits, it releases not only a large burst of energy but also additional neutrons. Those neutrons can then strike other uranium-235 nuclei, causing them to split and release more neutrons, which cause more splits, in a self-sustaining chain reaction that releases energy at an extraordinary rate. The scale of energy involved in this process is genuinely difficult to comprehend from everyday experience. A single uranium fuel pellet roughly the size of a fingertip contains as much usable energy as approximately 1 ton of coal. Not because uranium is chemically more reactive than coal, it is not, but because nuclear reactions release energy from the binding forces within the atomic nucleus itself, which are millions of times stronger than the chemical bonds involved in burning. This is the physical reality that the 20th century unlocked. And it led in two directions simultaneously, toward electricity generation and toward weapons, with consequences that are still unfolding today. In the early 1940s, a secret research program known as the Manhattan Project brought together the most concentrated assembly of physics talent in history, working under extraordinary pressure in locations across the United States and Canada. Their objective was to determine whether a nuclear chain reaction in uranium or plutonium could be made to proceed fast enough and at sufficient scale to produce a weapon of catastrophic destructive power. The answer, delivered over Hiroshima, Japan on the 6th of August, 1945, was unambiguous. The bomb designated Little Boy, fueled by highly enriched uranium-235, killed approximately 140,000 people. The world had crossed a threshold it could never uncross. Enrichment, the industrial process of increasing the proportion of uranium-235 in a uranium sample from the natural 0.7% to the higher concentrations needed for weapons or reactor fuel, became one of the most strategically significant technologies in human history. Enrichment to approximately 3 to 5% uranium-235 produces fuel suitable for civilian nuclear power reactors. Enrichment to above 90% produces weapons-grade material. The same basic industrial process, taken to different endpoints, represents the difference between generating electricity and constructing a bomb. This is the central tension of nuclear technology that international diplomacy has wrestled with for 8 decades. On the peaceful side of that fork, nuclear power plants use the controlled version of the same chain reaction. Uranium fuel rods are arranged inside a reactor core, and the chain reaction is carefully managed using control rods made of neutron-absorbing materials, which can be inserted or withdrawn to speed up or slow down the reaction as needed. The heat generated by the controlled fission heats water, producing steam, which drives turbines connected to electrical generators. The nuclear fuel itself never combusts. There is no fire in a nuclear reactor. There is only heat, generated by the splitting of atoms, transferred to water. In 2026, nuclear power provides approximately 10% of the world's electricity, operating in 32 countries across more than 400 reactors. It produces no carbon dioxide during operation, making it one of the lowest carbon sources of electricity available at scale, a fact that has renewed interest in nuclear energy as part of the global response to climate change after decades during which public concern about safety kept many countries from expanding their nuclear capacity. Uranium does not appear in nature in a convenient form. It is distributed through the Earth's crust in various mineral compounds, concentrated enough to be worth extracting in relatively few locations. The countries with the largest uranium reserves and production capacity include Kazakhstan, which produces roughly 45% of the world's uranium, Canada, Australia, Namibia, and Uzbekistan. Extracting uranium involves mining the ore through open-pit or underground methods, then processing it through a chemical milling process that produces a concentrated powder known as yellowcake, uranium oxide in a form that can be transported and further processed. The mining and milling process raises genuine environmental concerns, including the potential contamination of groundwater with radioactive and chemically toxic materials, and the health risks to mine workers from exposure to radon gas and uranium dust. Modern mining operations operate under strict regulatory frameworks, but the history of uranium mining in the 20th century includes episodes of significant harm to workers and surrounding communities, particularly involving indigenous communities in North America and Africa. The back end of the nuclear fuel cycle presents its own profound challenge. Spent nuclear fuel, the used uranium rods removed from a reactor after their fissile material is exhausted, remains intensely radioactive for periods that vastly exceed any human institution's lifespan. Managing this material safely requires geological repositories, deep underground storage facilities designed to isolate the waste from the biosphere for periods measured not in decades or centuries but in hundreds of thousands of years. Finland is currently the furthest advanced in constructing such a repository. Most other nuclear nations are still developing their long-term solutions, maintaining spent fuel in interim storage while the political and engineering challenges of permanent disposal are worked through.